I'm Barbara, this is Ansel. We've done CppC's and doxypress. What we're going to be talking about is compile time counters. In the process of doing CppC's, what we needed to do was we needed to do some registration for some metatype data. The problem was how to do this. It isn't practical to actually do all the code that you need to do and to write it all by hand. So we needed a way to automate this process. So what we came up with was a way that you actually do some information and then you chain everything. And in the process, let's go to the next slide. So in the process, what we actually want to do is we want to register some data and some metadata. We want to do that in CS register 0. And we actually want to register the data and then call CS register 1. We want CS register 1 to do something and call CS register 2. The problem is 0 and 1, let's just go off. 0 and 1 are values. They're not data types. And we're trying to use method overloading. So the problem is, how do you actually do this and use method overloading when these are numeric values and they're not data types?
And we put this slide in here for reference if anybody's unfamiliar with Constexpr. One of the things that we're going to be using in this talk is Constexpr very heavily, and it allows you to set up a value that is evaluated at compile time, so you can use it for things like the size of an array. We'll be using it in a slightly different context in a moment. So, as part of our solution, we had to use templates because the solution to every complex problem in C++ involves templates in some fashion. And what we need to do is we need to somehow have a value wrapped up as a data type. Now, usually when you're using a template, the reason you're using it is because you want to pass a data type as a parameter to some class or function or method or what have you. And the question is, can you pass an integer as a data type? And of course, you can. What not as many people realize is that when you define a templated data type based on an integral parameter, that results in a unique data type that's distinct from every other integer that you could pass to that templated data type. I've got a lag on this.
Back up one. Yes. So what we have here is this template, CSInt. And what we're noticing here is CSInt, the n-1.
So what this class does is it wraps up an integer inside a templated class. But more importantly, we've set up an inheritance relationship where 3 inherits from 2, 2 inherits from 1, 1 inherits from 0. Then we've had to specialize the templated class to stop the recursion at 0. Otherwise, it would just continue infinitely into the negative numbers.
So what you're looking at is one too many slides.
Yes.
So what we're looking at here,
Whoa.
That was exciting.
All
That's
right.
a lot of slides. We have a clicker problem.
Apparently.
So what we're looking at here is class Ginger. This is the beginning of the class. There actually is a macro in the real code. What we've done is we're showing the expansion here. We've left out some of the details. We're showing the main information. And we're showing this templated method.
Now, this templated method is what's going to catch the end of our chain. This is a templated method that's good for any integer value, and it will simply do nothing. The second part of this is we're declaring a method called CSCounter that takes a wrapped 0 and returns a wrapped 0. Hold on to this line. Remember it. We'll use it in a moment.
Notice we're still at the opening curly, so we're still inside this declaration. So now what we have here is we're assuming that there's another macro on line 42 and then a macro on line 43. We're trying to show just the snippets of code that actually make sense. So the first top part is what's expanded for line 42. The bottom is what's on 43.
And the question is, what is value 42 and what is value 43? Anybody care to hazard a guess?
And why? 42 is a good guess.
42, very good. Points for the reference.
So there's the static Constexpr, and we are doing an assignment of value 42. There's a decal type. There's the CS counter.
So the way that I like to look at decal type, and in this particular context, we're using an expression decal type. The way I look at expression decal type is it's a hypothetical statement. It's if I were to do this thing at this point in the code, what data type would it evaluate to? So in this case, we're saying if I were to call CSCounter with a wrapped 255, what would I get back? And the answer is, by the normal rules for method overloading, it would match the 0. And the reason for that is because 255 inherits from 254, inherits from 253 all the way down to 0. And therefore, you can successfully call the method that we declared on the previous slide. So value 42 will be 0. Then, on the following line, what we do is we declare a new overload of the CSCounter method that takes a wrapped 1 and returns a wrapped 1. Therefore, in the second half of the slide, when we evaluate value 43, and you'll notice that value 42 and value 43 are initialized with exactly the same expression. It is exactly the same expression, and it is Constexpr. However, value 43 will get the value 1. Because when the compiler resolves the overloaded method, 255 is slightly closer to 1 than it is to 0. Therefore, the overloaded method that will be found is the one we just declared that returns a 1.
The visibility of this is because it can only look up at this point. It can't look down. So it does compile, it does actually work. And so value 43 will be a 1. Now notice in here that we're doing the same type of a code. When you go to the next slide, what you're going to see is now we're expanding what really happened with 42. So again, with 42, we're at a value of 0. And what you can see is in the static void CS register, we're actually calling our stata-meta object register method. That's where we're actually doing what registration. We've put in some v values in here. We didn't expand all of the values simply because some of them got really long and it didn't fit on the slide. But then notice at the end of that method, this is where the chaining will take place. And it will call CS register passing a 1. So now the visibility is that it's calling something that isn't defined yet. So it's visible below.
So that becomes the question. If you look at the 2 highlighted points on the screen, I mentioned that in the first case, the compiler will only consider for overload resolution the methods that are already visible. However, in the second case, down at the bottom of the screen, we are able to call a method that has not yet been declared. Does anybody know why this is possible?
The standard defines when a class is complete. And most of us all know that at the end of the curly, a class is complete. This is one of the obvious cases. We also talk about that something is complete between curlies on an inline function. But there's a couple of other very obscure exceptions in the standard.
And it turns out that those exceptions work in our favor. The first exception, which I'll mention for completeness, is that after the equal sign that declares a default value for a parameter of a method, the entire class is considered complete, and therefore you can refer to things that have not yet been defined. The other location where it is defined to be complete is after the equal sign of the default initializer for a non-static const member variable. And this becomes very important because if you'll note at the top of the screen, what we have is a static const member variable, which means in this context at the top, the compiler is not permitted to look at any methods that are declared below that line for purposes of evaluating that decal type. However, inside the method at the bottom of the screen, the compiler can see the entire class, even methods that have not yet been declared.
So this is allowing you to actually create a counter based on runtime information and allows us to do a concatenation. What this did is it gave us the ability to set up everything, to have the macros that we established, and it actually went through and set up everything, and then every time we instantiate a class, the registration happens automatically. We don't have to keep track of the count. It was pointed out to us the value of 255. That is a Clang limitation which can be overridden by a parameter. But the truth is, this code gets optimized in a very amazing way. We actually looked at the assembly dump on a lot of this.
And speaking of Clang, if you compile this code with Clang, my hat's off to their optimization team.
Amazing.
Because this code is compiled and optimized in the most amazing way possible. The entire integer wrapper disappears. All of the overloaded methods disappear, and it tail call optimizes all of the CS register methods together. So this is a zero overhead mechanism for chaining method calls together in the body of a class. And we believe that this is a useful technique. If you should ever have a need for it, you can actually store a counter in the overloaded method table of your compiler, and it will work. It's standards compliant in C++11 and anything later.
It still works, obviously, in GCC. Their optimization isn't quite as excellent as Clang, but it's still really good.
In the GCC implementation, all of the extraneous parts, the integer wrapper is optimized away. However, it's not quite smart enough to see through the tail call nature of these methods, so you do end up with separate registration methods for each integer. Not quite as low overhead, but still quite impressive.
And just in case anyone's curious, CppCr and DoxyPress, everything's available off of our website. We're available for questions and to go over any of this code in case anybody wants to chat with us about it. And we hope you'll take a look at both CppCr and DoxyPress. Thank you.